Okay, so we have a sort of a notes problem that we can put into your notes because it's a good explanation of how momentum works. So in this case, a hunter spots his prey off to the right. He waits patiently and does not move. When the hunter fires, the bullet has a momentum of 284 kilogram meters per second. I just want to point out something real quick here. The unit of momentum, kilogram meters per second, that comes from the idea that momentum is mv. So the kilograms come from the come from the mass, and the meters per second come from the velocity. So you know how force has this really nice little handy unit called a newton, which is actually a kilogram meter per second squared. There's no sort of handy dandy little unit for momentum. It really is just a kilogram meter per second. There's no way to shorten it. Anyways, moving on. Any hunter or anybody who's fired a gun will tell you that there's kickback, and that's because of the conservation of momentum. So what we're going to do right now is we're going to solve this problem using the conservation of momentum ideas. Now, the way we do those is that we always think about the momentum before is always equal to the momentum after because it's conserved. Just like energy, the total energy before is equal to the total energy afterwards. And it's possible you lose some energy or gain some along the way, but that's accounted for with work. Here, the momentum before and momentum after. Now, what's the system? Now, what are the two objects that comprise the system? Well, it's going to be the hunter and the bullet. So we're going to say the momentum of the hunter plus the momentum of the bullet before has to equal the momentum of the hunter plus the momentum of the bullet after. Now, obviously, for future problems, you probably won't have to write out every single step like this, but I'm teaching it, so just give me a break. Get off my back, okay? Now, before you pull the trigger, what's the momentum of the hunter? Well, before you pull the trigger, remember that momentum is equal to mv. The momentum of the hunter, the velocity of the hunter and the velocity of the bullet are both 0. They certainly have mass, but again, their velocities are 0 before you pull the trigger. So, the momentum of the hunter, I'm going to just call it h for right now, plus the momentum of the bullet afterwards. Now, it says that the bullet has a momentum of a positive 284. I'm going to leave off the unit for right now. So, but the way you want to think about this is the bullet has momentum this way. The hunter is going to have momentum this way. So we got to be careful with our velocities. Velocity have plus or minuses depending on the direction they go. So we would expect the velocity of the hunter, the momentum of the hunter to be negative because he's going to have a negative velocity. You can't have a negative mass, but you can have a negative velocity. Now this question doesn't ask for, what is the velocity of the hunter, because we would have to know the mass of the hunter to figure that out. But all it's asking for is a momentum, and that's going to be easy to do. So you can tell pretty quickly that the momentum of I'll just skip that step. I'm running out of space on the slide. That in order to equal 0, the momentum of the hunter has to be equal and opposite to the momentum of the bullet. Okay, so that's how we would do sort of a really basic conservation of momentum question, just understanding that the total momentum before has to equal the total momentum afterwards. In this case, we were not solving for velocities, we're just solving for just total momentum. So let's go to a problem where we're a little bit maybe more interested and solve it in terms of the velocity. So let's jump to this one. So here we have playing a game of pool, and the cue ball is going to hit this ball, which is at rest. After the two balls collide, the four ball has a speed of 2 meters per second. And notice that this is 3 right here, so I'm just going to quickly switch this to 2. I remember that now with this slide. I've never gotten around to changing it. So after they collide, this thing's going to be going here at 2 meters per second. And we're trying to figure out the velocity of the cue ball. Now, if we pause for a moment, anybody who's played pool will tell you that sometimes the cue ball, I'm just going to draw this on the top here, that sometimes the cue ball, when it hits something, sometimes the cue ball follows after it, but then also sometimes the cue ball bounces back. So you can imagine some situations where the final velocity of the cue ball might be a positive, and there might be some situations where the final velocity of the cue ball might be a negative. The good thing about the conservation of momentum will tell us exactly which direction the cue ball is going to go. So that's another cool thing about physics, is we can figure out which direction this thing is going to go. So we're going to set up, with this limited space here, I'm just going to, zoom in a little bit. The total momentum of the system before, I'm just going to write it up here. So P before has to equal P after. Now we have two objects. So M, I'm going to call this cue ball, V cue ball plus, and we'll call this the 4 ball, M4, V4, beforehand has to equal the MQ, VQ plus M4, V4 after. All right? So the total momentum before has to equal the total momentum afterwards. The total momentum before. The total momentum before was 0.17, and its velocity was a positive 3. This ball was at rest. So that's just going to simply be 0, because its velocity is 0. So all of the momentum of the system comes from the cue ball. That's going to be split up or divided between the two balls after the collision. So we're trying to figure out what happens. So we don't know what happens to the velocity of the cue ball afterwards, but we definitely know what happens to the velocity of the 4 ball. And again, it's given as a positive 2. I mean, it would be weird to imagine that this ball hits this way and somehow this thing comes back. That would be kind of weird. So anyways, now it's just really a calculator problem. We have 0.51 equals 0.17 velocity of the cue ball plus 0.32. So 0.19 equals 0.17. All right, now it looks like it's going to be slightly over 1. Let's figure out what it is. 1.12. So turns out that this is a follow-through type of a question where after the collision, this ball will continue moving straight ahead, but it's going to slow down, right? It was going 3, but it gave away some of its momentum to this 4 ball, and now it's only going to go at 1.2 meters per second. All right, and that's how we do a couple questions on conservation of momentum.